This experiment is about Archimedes' principle, and as you know, that states that when a body is immersed in a fluid, there's an upthrust which is equal to the weight of the fluid displaced, and this upthrust produces an apparent loss of weight in the object. Now we're using water, so the upthrust will be equal to the weight of water displaced. We're also going to use the calibration graph from our stretching of a rubber band experiment, and I've got that set up here. So the elastic has stretched, we've got a piece of stone on the end, actually it's marble. The extension of this band is equivalent to 13 centimetres, and that from the calibration graph would mean a mass of the piece of marble of 157 grams, or a weight using G equals 10 of 1.57 newtons. Right, we're now going to put the stone in water. There's our water, and we're going to lower the stone in, make sure it's all nicely balanced. Now, the rubber band in this case has not extended so much. In fact, it's 6 centimetres, and that, if you looked at the calibration graph, is equivalent to a mass of 100 grams or a weight of 1 newton. Therefore, what's the apparent loss of weight? Well, 0.57 of a newton. Now, that's equal to the weight of the water displaced. But water has a density of 1,000 kilograms per cubic metre, so the mass of water displaced would be equal to 57 grams. So, what is the density of the stone? Well, since water has a density of 1,000 kilograms per cubic metre, we know that 57 grams of water have a volume of 57 cubic centimetres. Therefore, if we divide the mass of the marble, 157 grams, by the volume of the marble, which is 57 cubic centimetres, we get an answer of just over 2,750 kilograms per cubic metre. That's the density of the stone. Now, you need to think about the accuracies of different parts of the experiment, but we are of the right order. That's a reasonable result for the density of the stone.